Electronegativity and polar bonds. We have looked at ion formation and ionic bonds, where electrons move from one atom to another to form ions, and oppositely charged ions attract each other to form crystals. And we have discussed covalent bonds, where electrons are shared between two atoms to form molecules. However, electrons are not always shared equally between atoms in a covalent bond, even if they are not transferred completely from one atom to another. Covalent bonds in which the electrons are not shared equally are called polar bonds. I like to explain unequal sharing of electrons with an analogy. Say there are two siblings. I'll call them Robin and Chris. They have a ball. Robin is 5 years old and Chris is 3. Who do you think has the ball more of the time, the older child or the younger? In my experience, it would likely be the older child. Mom calls from another room. Robin, are you sharing with Chris? Robin says, yes, Mom. But Robin's idea of sharing is to bounce the ball off of Chris's head. Chris may have the ball occasionally, but the sharing is not equal. The unequal sharing in a bond means that one side of the bond is more positive than the other side of the bond. The bond has a positive and a negative pole. Note that these are not full ionic charges, but partial charges, indicated by a lowercase Greek letter delta. If a container of, for example, hydrogen fluoride gas is placed in an electric field, the molecules will all line up with the positive ends pointing toward the negative electrode. But how do we know whether a covalent bond will be polar or not? To answer that question, we need a concept called electronegativity. Electronegativity is the tendency of an atom to hold on to electrons. More electronegative elements hold onto their electrons more tightly than less electronegative elements. This is not a measurable quantity. The scale was developed by Linus Pauling. He compared the bond energies of atoms when bonded to another atom of the same element versus bonded to an atom of a different element. For example, comparing a hydrogen-hydrogen bond, a fluorine-fluorine bond, and a hydrogen-fluorine bond. The hydrogen-fluorine bond energy is not the average of the other two bonds. It is stronger. Pauling attributed this difference to ionic character in a covalent bond, a polar bond. He developed his scale of electronegativities based on arbitrarily assigning fluorine a value of 4 and comparing bond energies, first to fluorine compounds and then other compounds. The electronegativity scale is for atoms in bonds, not atoms alone, although each element is assigned a number. The noble gases generally don't have electronegativities listed, as they tend not to form bonds. But why do some elements hold more tightly to electrons than others? To answer that, we are going to look again at the Bohr model of the atom and the concept of shielding. Recall that electrons in an atom are in different energy levels, or main shells. When one shell is filled, electrons begin to fill the next higher energy shell. If we start with hydrogen, it has 1 proton in its nucleus and 1 electron in the first shell. That negatively charged electron feels the pull of the single positively charged proton. Now look at helium. We will disregard the neutrons since they have no charge and do not affect the electronegativity. Helium has 2 protons and 2 electrons. Both electrons are in the first main shell, effectively the same distance from the nucleus and not interfering with each other. Each electron feels the full attraction of both protons in the nucleus. The helium nucleus pulls more strongly on its electrons than the hydrogen nucleus does. Moving to lithium, with 3 protons in the nucleus, the first 2 electrons are in the first shell, but the third electron has to go into the second main shell. The two inner, or core electrons, are now shielding the third electron from the nucleus. They are closer to the nucleus and in between it and the third electron. The third electron, the valence electron, only feels the pull of one proton because two of the positive charges are balanced by the negative charges of the two inner electrons. Moving on to beryllium, the nucleus now has 4 protons, but the number of core electrons has not changed. Each of the 2 valence electrons now feels the pull of 2 protons. These valence electrons are held more tightly than lithium's 1 valence electron. The beryllium is more electronegative than lithium. Similarly, the valence electrons of boron, carbon, nitrogen, oxygen, and fluorine each feel stronger and stronger pulls from the nucleus because the number of core electrons does not change, but the number of protons increases. The shielding is still only at 2, but the nuclear pull keeps increasing, and the valence electrons are all in the same main shell and not interfering with each other. The electronegativity increases as the nuclear charge increases, as long as the number of core electrons does not change. Electronegativity increases as we move across a row of the periodic table. Once we get to sodium, we once again only have 1 valence electron, as the second main shell is full, and sodium's 11th electron goes into the third main shell. Now there are 10 core electrons shielding the nucleus from sodium's single valence electron, and the electronegativity drops. Now let's compare hydrogen, lithium, and sodium. Each of these atoms has 1 valence electron, but those valence electrons are in different main shells. The second main shell is further from the nucleus than the first. Likewise, the third main shell is further away than the second. As the number of the main shell increases, the distance from the nucleus also increases. Electrons, which are further from the nucleus, are not held as tightly as electrons which are closer in. So electronegativity increases as we move up a column of the periodic table. This table shows the general trends in electronegativity on the periodic table. As the color of the elements on this table change from yellow through orange to red, the electronegativity goes up. As you can see by these colors, electronegativity increases as you move up a column, and it also increases as you move to the right along a row. The most electronegative element is fluorine, and the least electronegative element is francium. Notice that the trends are not perfectly smooth, especially in the transition metals. Recall that the Bohr model of the atom has been superseded by the quantum mechanical model. While multiple electrons may be in the same main shell, they are spread out into different subshells. The subshells do not strongly shield each other from the nucleus, but there are some effects on the d electrons, which account for the variations in the trends across the table. If you look just at the main group elements, those in the S and P blocks, the trends are clear. Electronegativity can be used to predict the type of bond 2 elements will form. If the difference in electronegativity between the 2 elements is very small, from 0 to 0.5, the bond is considered pure covalent, with no ionic character. If the difference is between 0.5 and 1.5, the bond is covalent with some ionic character. It is a polar covalent bond. If the electronegativity difference is greater than 1.5, the bond is considered ionic. Note, however, that there are some bonds that fall in a gray area. For example, Aluminum has an electronegativity of about 1.5, and sulfur has an electronegativity of about 2.5. So the difference is in the polar covalent range. But aluminum sulfide is considered an ionic compound. It has a crystalline structure and a very high melting point. It is also formed from a metal and a nonmetal. Likewise, several compounds with nonmetals and fluorine have electronegativity differences of greater than 1.5, but are considered polar covalent since they are formed between two nonmetals. While we might like things to fall neatly into categories, the world doesn't always work that way. To summarize, some bonds fall in between ionic and covalent. These are polar bonds, where the electron sharing in the bond is unequal. One side of a polar bond has a partial positive charge, a positive pole, and the other side of the bond has a partial negative charge, a negative pole, causing a charge separation across the bond. Polar bonds are caused by unequal distribution of electrons, which is because different atoms pull on electrons with different strengths. The strength of pull of an atom for its electrons in a bond is called electronegativity. Electronegativity can be predicted by looking at how many core electrons are shielding the valence electrons from the nucleus. Electronegativity increases from left to right along a row of the periodic table and decreases from top to bottom down a column of the table. Two atoms whose electronegativity difference is very small, less than 0.5, form purely covalent bonds. Two atoms whose electronegativity difference is between 0.5 and 1.5 form polar covalent bonds, and two atoms whose electronegativity difference is greater than 1.5 form ionic bonds.